Welcome everyone to building a self-driving RC car. Let me start with a question. Please raise your hand if you would like somewhere in the future to own a self-driving car. So a car where you just sit in that will drive you from A to B. All right, I'll ask again after this session and we'll see if you still have the same idea. So do you know these conference talks where a speaker or two speakers get on stage and then they start explaining and give a little context and then doing a little demo and then you need to wait 15 minutes for the entire attention to build up and in the end you get the demo where you see everything you've learned in the entire session and you're waiting for 49 minutes and then it all gets explained in 1 minute. So we won't keep you waiting for 15 minutes because we'll start with a demo right away. So that afterwards we are all relaxed. There's no tension about exciting demos. We'll start with the demo and then explain how we did all this. So, because it was a bit hard for us to bring all the stuff, we have a recording of the demo that we will show you.
Let me show you how it went.
Control it. We'll talk all about this later. And the objective now is that I will start the car. It should drive itself, stay between the white lines, and then stop when it's not seeing any lines anymore.
So if everyone will cross their fingers now, right? See if it works.
If you're up front, I would advise you to lift up your legs.
So you're all safe now?
Well, we have an idea what's going to happen, but unexpected things happen all the time. So let's see, when we're connected. Here we go.
So, let me stop that.
So that was a bit scary. Actually, it was one of the scariest demos we've ever done, because typically when we do a demo at a conference, we have our hands on the keyboard and we control what's going on. In this case, we couldn't do anything, so we just fired it up and kept our hands up and then needed to see what was going to happen. So we'll tell a bit more about how this went later. Let's first be nice and introduce ourselves to you. So my name is Bert Schrijver. I work at J-Point in the Netherlands, where we typically do consulting and contracting jobs for various clients throughout the Netherlands. I also work at OpenValue, which is a small Java startup. My current assignment is at the Dutch National Police, where I will be telling nothing about, and I run the NLJUG, which is the Dutch Java User Group. And I'm here together with
Tim van Eijndhoven. I also work at J-Point, and I'm also currently hired by the Dutch National Police. So, Bert-Jan, please tell us, how did we get started?
Yes, so is this our job? Do we build self-driving cars for a living? Well, I'm glad we don't, because probably we would be out of business fairly soon. So we typically do fairly serious stuff, consulting work for clients. We're building typically Java-based web applications. And every now and then we want to do something completely different. So we gather around with the whole team for a hacking in our office, and we work maybe on an open source project or a hobby project or whatever. So in this case, I think actually one of our bosses came with the idea to set a challenge to build a self-driving car. So we call this the Robo-Race Challenge, and we set out with 4 teams who had the challenge of building this car and competing with each other. So the rules are, each team gets a basic RC car kit, which is something you can pick up for around €200, which has an engine and a battery and a steering servo and wheels. And you get a fixed budget to put electronics and sensors on the car to make it autonomously driving. Then there are 3 races. The first is just a simple drag race. There's a course of 50 meters where your car needs to watch a starting light. It needs to stay for 50 meters between 2 lines and then stop in a stopping zone. Second race is more of a bit of a racetrack, so there's corners involved. And the third race, we haven't come this far yet, is multiple cars on the track, and then cars also need to avoid each other if we ever get there. So let's talk about the basic car kit. It's something that you can buy if you are building an RC car, and there's lots of stuff already going on there. So there's wheels which are useful for driving. You wouldn't guess, but they are. There's a steering servo that will steer the wheels. There's a battery in there. There's some suspension. What you typically do is buy this and then plug in a wireless receiver and then buy a remote control that connects to the receiver and then control the car. But we need to make it smart. So we put some electronics on there, a Raspberry Pi. Because every project gets cooler when you throw in a couple of Raspberry Pis, right? So we put a Raspberry Pi on top of it, and it needs to get power. So it gets power from the car battery by some unidentified component we ordered in China that converts the battery current from 7 or 12 volts to 5 volt USB. So then the Pi could be powered from the car battery. Then we need to run something on there. So we chose Vertex for this. How many of you have heard of Vertex before? Okay, about 1/3, I would say. Vertex is it's a fairly general purpose toolkit for building reactive application on the JVM. It is event-driven, it's non-blocking, and it's general purpose, so you can basically build anything with it. So at one of our previous clients, we were building web applications for an educational publisher, but you can also run it on a car. So why did we choose it? A couple of reasons. It's fairly lightweight, both in terms of resource usage and also in terms of disk space. It is polyglot, so we had the idea at first. There were a couple of front-end developers who also joined the team, that maybe we can write some parts in JavaScript and some parts in Java. In the end, we ended up writing only Java. And the most important thing is there's a distributed event bus. So whenever you run multiple instances of Vertex, they cluster together, but even over the network, and you get an event bus that you can use to send messages between the different components. And this enables us to run a small piece of control software on the Pi, and then connect to it over Wi-Fi and run all the rest on our Mac. And this makes debugging and deployments a bit easier. So I would say that the event bus was the biggest feature that we gained from Vertex. So if you want to learn more about Vertex, I did a talk about it once. It's up on YouTube. I would say it's a pretty cool framework to work with as a developer.
Definitely.
So then we need to hook stuff up. So we are there. Usually, when you put in your wireless receiver, there are a couple of wires that go in there. A couple of wires go to the speed controller, and a couple of wires go to the steering servo. So what we did is not put the wireless receiver in there, but connect those wires to the GPIO ports of the Raspberry Pi. So you can see some cables running from the GPIO ports to the steering servo, which is something below here, and to the speed controller, which is somewhere below here. So a servo is basically a simple motor that can go in both directions, and that you can set at a specific angle. So this is useful for controlling the wheels. The speed controller is a device that you can use to control the amount of current that goes from the car battery to the engine. So maximum positive current is maximum speed ahead, maximum negative current is full speed reverse, and somewhere in between is somewhere in between. So we connected those devices to the GPIO ports of the Raspberry Pi, and GPIO stands for General Purpose I/O, which stands for General Purpose Input/Output. So these are fairly general purpose pins. There's a schematic that you can look up, and these pins have numbers, and they either power 5 volts or 3 volts, or there's a data pins, and there's ground pins. So typically one device has power, ground, and a data pin. And this is all you need to control a servo, speed controller, but also other devices you connect to these ports. We were powering them with 5 volts, I believe, because that's how these devices work. So then they are connected, but now we need to understand each other. We need to make the Pi emit signals that the speed controller and the steering servos will understand. So this turns out to be PWM, which stands for pulse width modulation. And these are basically pulses that get sent out over the wires, and you vary the width of these pulses, and you can use this to put a data signal on these wires. So in our case, it was a signal, I think, between -256 to +256 that we could use to either control the engine or control the steering. And we did a little bit of digging about how to send these signals on Raspberry Pi. There's a utility called Servo Blaster, which is up on GitHub, which you can download, and then you'll get a Linux device, Dev Servo Blaster, where you can echo commands to. So echo 1 is 200 greater than Dev Servo Blaster. We'll send the character 200 to Servo Blaster device 1. And then there's a schematic that says, all right, if you want to control servo 0, hook it up to GPIO pin 4, GPIO number 4, and plug these pins. So this was fairly easy to get working. And I would say that I think within half a day or so, we could, by echoing commands on the Pi, control the wheels of the car. We noticed fairly quickly that when you're making stuff that drives that you need to worry about safety. Well, not really our own safety, but the safety of our car. Because our first prototype was Raspberry Pi on the car, Linux on there, Wi-Fi stick on there, Mac connects to the Pi, we SSH into the Pi, and we type in the command line, echo 3 is 251, greater than dev servo blaster. This would set the wheels to course. Maybe we wanted to drive. We said echo 4 is 200, greater than dev servo blaster, and this would send the speed to the speed controller. So when I first wanted to make a drive, I made a typo in the command that I sent to the speed controller, and it burst away at max speed to the other side of our office. Luckily, there's a big rubber bumper in there, which we I think save lots of trouble for us. But it went away so fast that I was typing the commands to make it stop, but it was already out of Wi-Fi range. So so then we needed to run. That was the only option. So we figured out pretty soon that we needed some safety mechanisms. So what we did is build a heartbeat that sends from the Mac that controls everything a signal, I don't know, every 200 milliseconds or so. And as soon as we haven't received 2 of those heartbeats, so we can have 1 packet drop on the network, as soon as we haven't received 2, then it will shut down the engine and stop. And that turned out to be fairly smart thing to do. Then we needed the car to have eyes. So we bought a Raspberry Pi camera, which is also fairly cheap, I think around 30, 35 euros. You plug it in 2 pins on the Pi, you have a camera working. Now we need to get a video stream, and we use the Raspberry Pi Cam web interface for, which surprisingly is a web interface for the Raspberry Pi Cam. So you can, it's also free on GitHub, you can install it, it fires up a web server, it connects to the Linux video device, and then you can stream video from either through a web page or maybe through MJPEG or MPEG-4. And there's a web interface you can use to control the video settings, so stuff like brightness, contrast, white balance, and this turns out to be fairly useful for us. So I would say that we are almost ready to go. So we have the car, we can control it. We have so Vertex and Java running on there. We have some control software on the Mac. We have video stream from the car. If we put everything together, it kind of looks like this. So we have a small legend here that says things like up is faster, S is brake, R is center. I don't know, some arbitrary stuff. Here we see the logging from the Vertex event bus. Coming by, so this is all the stuff that the Pi sends back and that we are sending to the Pi. Here we have the camera image that we're seeing, and now we can basically manually control it by using the keyboard, making the car drive, and looking at the camera what's going on. But then there are some other lines here that might have some use, and I think it's about time that Tim tells us something about how we make the car drive itself.
Right, so now we had all the hardware, we had the software set up, but now we needed to let the car drive itself. And in order to do that, we had to enable it to take the video feed from the camera, analyze it, and understand where it is in regards to the road and its goal. So we needed to do image recognition or image analysis on it, computer vision, if you will. And we went on the internet because it's not our day job to do computer vision stuff, so we're pretty new to the field. So we went to the internet to find out what would be the best solution for us to use. It turns out that OpenCV is one of the largest used frameworks for computer vision. It also has machine learning capabilities, and it's so widely used that its algorithms with regards to computer vision are heavily optimized, and there are many resources available. And I think the last thing is the thing that helped us the most in order to find examples on how to do certain steps in an image processing pipeline by examples. Important thing is, as well, it's written in C++, but it has Java bindings via JNI, so that helps when calling it from Java, which is our language of choice. So, in order to take the image from the camera and to know where the car is on the road, we do a number of processing steps. And the first one is an edge detection. So we need to find out where the lines are in order to know where the road is. And to find lines, it's often best to start with detecting edges. So we find the inner and outer edge of both of the lines, left and right. This algorithm is called Canny, and it's been around since the early 80s, so it's quite an old algorithm, but it's still very widely used in order to detect the edges. Now, a Kenny algorithm serves as like a binary image, like it's a 1 and a 0. So a 0, there's no edge at this pixel. A 1, there's an edge at this pixel. And but these are just 1s and 0s. So we need to understand which 1s and 0s are actually connected into what we call a line. And in order to do that, we use the U-line transform. It comes in two forms. One is a normal U-line transform, and one is a probabilistic version. We chose a probabilistic version, not because I understand what it does, but because it was named fastest on the internet, so I thought that would be best, right? And when the U-line transform runs, it will find the actual lines in the image. And what you will notice is, in the top right, it actually finds a horizontal line here as well. But we're only interested in the left and right line in the image. So what we do in the third step is take these lines that we got back from the algorithm and then filter them. We filter them based on mainly on their angle, because we know we're looking when the camera looks straight forward, we have two parallel lines where the car is in between, and we know that they will converge at the end, right? So we can take the left line as being a line between a certain angle with some margins, and the right line as well. So that way we can filter them. We thought it would be a good idea to take like the average of the lines, to see the middle of the line. That's not really necessary. I mean, you can also take like the innermost line of both of them. But then we know where the left and right edge of the road is, and based on those two lines, we can determine where the center of the road is actually. And that was the thing that we used to see where the car is with regards to the road it's driving on. So when we go to the code to see what this is like, switch out here to IntelliJ. So we have a bunch of code, but the basic part, our image processing pipeline, is in a class that we call the image lane detector, because basically we have a video camera which sends us a video feed, but a video feed is nothing more than just a sequence of images, right? So we sample every 100 milliseconds one of those images out from the feed, and then we will do the image analysis on it. And what we do first is actually reduce the amount of the image that we will actually process. Because we know the camera is looking straight forward on the car, there will be a horizon somewhere in the image. And everything above the horizon is not of interest to us. We are only looking for the lines which are on the surface. So we can quickly cut off the top part of the image. We do not need to process it. At first, we basically took the lower 50% of the image to analyze. When we started to actually navigate corners, we went a little bit further ahead, looking at the lines, because we had to predict where the car had to go in the future. So we reduce the image size, and this is really important because the lesser pixels you have to process, the faster it will be. So the reduction of the amount of image to be processed is an important performance factor. Now that we have the region of interest, we have what we call the line extractor, and it takes two classes. So the first class is our wrapper around the Kenny algorithm, and the second one is the wrapper around the U-lines algorithm. Now, in order to show you how easy it is to use OpenCV for this, I will show you the classes. So first, the Kenny edge detector. Now, there are a number of parameters that it takes to, which are parameters to the algorithm in order to tune it. But the actual work is done in this line. It's just a one-line call into the OpenCV library with the original image, which will present us with the binary image. There's an edge here, yes or no. So that's really easy. The U-lines detector is basically the same. It has a bit more code because we want to go from the data structures that are used in OpenCV to a data structure that we can use in order to do our own calculations. But the real processing is done, again, in this one line. So we present the result of the Kenny transformation into this function, and it will provide us back with a set of lines or vectors. which we can then use to do the rest of our analysis. So then we have a collection of these lines, right? So now we are at step 2 of the images. Then, in order to filter out the lines that we no longer need, we use what we call the default lane detector, and this basically contains the filters to filter the left and the right lines based on their angle. And it can do some calculations. So we then have the lines, and we can calculate the parameters that are important to us to know how to steer the car. So what we do is we calculate the angle under which the car is with regards to the road, right? Is it facing to the right or to the left, or is it straight forward? And we measure the distances to the left and the right side of the road. This gets put into a data structure, which contains all these values, and then we will send it, or the function calling this one, will send it over the event bus to the process that will actually analyze these numbers and say, well, that means that we have to steer left or right at this point by this amount. So basically, in order to do this image pipeline, it's 2 calls into OpenCV. But now we have some code, but I mean, when you're programming, you have to have a proper architecture, right? Everyone needs proper architecture. So we sat down and we thought, well, let's design an architecture. Spoiler, this is not proper architecture, okay? It's an architecture, it's not proper. And I will tell you why in a minute. Now, first off, these names in the processes, do they mean anything to anyone? The Dukes of Hazzard, that's right. So when we formed the teams, we decided it would be cool to call our team the Dukes of Hazzard. And when we decided on the architecture, we thought, or, well, let me take responsibility. I thought it would be a brilliant idea to name all these processes after the characters in the Dukes of Hazzard series. So every process gets a name of a character, right? And then we have this event bus, and they can talk to each other. So that would be awesome, right? It turns out it's not. Because the file that we access the most in our project is the README file that tells us which name, which character does what function in our system, right? It's insane, but okay, anyway. Let me explain to you. So basically we start with the camera, right, which has the image feed, and it feeds it into the process called DAISY. This is where the code lives that I just showed you. So DAISY has the image processing pipeline. In order for us to understand what is being done in this pipeline, we have another process which ties into it and takes all the intermediate results. So the result of the Kenny detection and the result of the U-lines detection are all extracted from DAISY so that we can present them in our UI, so that we can understand what the algorithm is doing. Why is it not seeing lines? Why is it deciding to go anywhere, not where it's supposed to go, right? The other thing is that the data structures that are created, so with the angle and the distances, is sent over the event bus to a process called Luke. And Luke was the character in the show that was the smart one. That's the smart one of the 2 brothers driving the car in the series. So Luke is the one that understands what needs to be done when the car is under a certain angle. And it will tell the process running on the car, Bo, to steer left or right, or to accelerate or decelerate. This will then send via the servo blaster system that we showed you commands to both the steering servo, making the wheels go left or right, and to the engine, making it go faster or slower. And there are 2 other processes running. So one is Flash, which is the system checking the heartbeat. Right. So this is the safety mechanism running on the car. When Flash does not receive a heartbeat for or 2 or 3 heartbeats, it will shut down, or it would tell the engine to set the speed to 0 in order to stop the car. And it powers the beautiful LED that we have on the rear of the car. And then we have one process called Boss Hog, and this is basically our UI. So this is the thing that allows us to send our manual commands to the system. Now these processes are running on a laptop, and these 2 processes are running on the car. So that's a beautiful architecture. It's not a proper architecture, but it looks lovely. I mean, this car has to be awesome, right?
It is awesome. And we have kind of this expectation that, well, we've now built the next Tesla. We have a Tesla killer. Our car will be in stores next year and Tesla will go bankrupt. Well, in reality, our car is more like this. So, you know, it drives, it does a bit of driving, but, well, it could be a bit better. So, and we have some video to prove how well it drives. You get to be the judge. So this is, I think, actually recorded in my kitchen, where we did the first full integration test of our system. So we have the starting light here, and when this light goes off, the car should drive, stay within lines, and then stop in the stopping zone. So here we go, fingers crossed.
All right.
This was a huge milestone for us.
Huge success.
I'm happy that you're applauding because we were screaming in my living room, and this where first stuff got to work together a little bit, and then we did a bit more a longer test, which is in the hall that's next to our office, where we need to make sure that it could also navigate through a bit longer lanes. So here we go. So you can see that it's starting to swerve a little at the end. And this is a traditional feature of a feedback system. So we're currently navigating based upon the angle, and we overcorrect a little. So then we need to overcorrect a little back, and then we end up here. So we start swerving. And I think in one of our previous sessions, somebody mentioned this autonomous drunk driving. So that's kind of where we are. And it's the result from the fact that we're constantly steering based on the angle that the car is making. So we were practicing this here, and there's a big hall next to our office that's often used for expositions. This time, I think there was a baby exposition.
Yeah,
so
right.
You can go there and you can find all the stuff you can buy for your yet to be born child. And we were practicing here in this alley, and then for some reason, the car found this small passway here.
It's a beautiful road, right?
Yeah, so it drove straight, it made a 90-degree turn, and it went straight into here, onto the baby expo. So I needed to run after it. People were shouting, "Wow, there's a drone!" And I needed to run in there to fetch the car. So what happened? Well, we don't really know. Maybe it thought that this were two nice white lines that it should follow. We're not really sure, but you know these things happen. And then this is a video of a bit longer trajectory with a bit more lighting conditions. So we found that the car is very susceptible to different lighting conditions. So shades, maybe it gets dark. We're not detecting any lines, we're basically blind, so we can't see anything. So we made a couple of parameters, you might be able to see them here, that we could tweak some parameters for the edge detection. Let's see how this goes. So the car is now driving through our office to the most important place of the office. The bar, obviously. So this was fairly well. Did we record this in one take?
Yeah, who thinks we did this in one take? Oh wow, such confidence.
Nobody? Come on,
confidence.
trust us. We've shown you what we've done, and still you don't trust us? You're absolutely
right.
correct. This took about 10 takes, and stuff like this happens all the time too. So what happened here? Who has an idea what happened? Reflection, yeah, that's actually, it took us a few iterations of this talk before people started suggesting this. The car is actually nicely between this line and this line. So it's doing fairly well, but this wasn't what we were expecting. So then it was time to race. So we had practiced the entire day. The car was driving nicely between the two lines and stopping in a stopping zone. This was all doing well. And then for some reason we had decided that we needed to do the race during the night.
Yeah, it was a brilliant plan.
That was a great idea. So lighting conditions completely changed. We needed to drive in cars to have enough light, and then it was really bright and then dark and shades, and this was a disaster. So there were, of the 4 teams, one team didn't drive at all. One team, the car was built by, there was a group of front-enders. Their car looked awesome. It had LEDs on there. It was fast. It was beautiful. Could it drive autonomously? No. They did have a cunning plan, though. They had the idea of setting it to a set speed, setting it straight, and then measuring how long it would take to go to the end, and then cutting off after exactly 16.3 seconds. Which was clever, but didn't really work. So there were two teams left. So we were left, and then one of our colleagues, Gijs' team, were left. And actually, the team of Gijs was performing a little bit better. And when we were doing the race went like this. So Polar car started about halfway. The car from the team from Gijs switched lanes, kept driving, stopped in the stopping zone. Our car drove like 15 centimeters further and then departed the lane. But the rules clearly stated that the car that drives the furthest in his own lane should win the competition.
Right.
So we won, yay! But actually, I think the car that the team from Gijs has produced was a bit better. So, are you around, Gijs? Are you here?
He's there.
Gijs, come up front. Come up front. So, guys, give a round of applause for our colleague Gijs, who actually had a better car. So, Gijs, we didn't bring the trophy, but we want to congratulate you because actually you won the second race. Another round of applause for Gijs, please. So then, after the race, we did nothing for a while, and then we went to work on it a bit more. And the first thing we did was change the way that the car steered. Because at first we were still steering based on angles, and from day one, Tim had been saying to me, we need to stop looking at angles, we need to look further, we need to look at the horizon. And I was like, yeah, you're right, and didn't do it for no obvious reason.
Minimum viable product, was it, right?
Yeah, sure. Yeah,
right.
It was working. So what we did is try to look as far as possible. So try to see where the two lines from the side of the road cross each other, and that should be somewhat our point on the horizon. And then just steer to that point of the horizon. And that worked surprisingly well. It worked so well that when we first started out on a straight track, we thought that the car was broken. Because we set on the track, it drove straight to the end of the track and then stopped. And we're like, well, it's not steering at all. So then we put a little bit aside, and then it still drove to the end of the track. So that worked fairly well. In addition, we had also added a bit more parameters to tweak the lighting. So brightness, contrast, white balance. So you can see a lot more sliders here to the left. And we're now testing this here in a bit more difficult conditions. So a bit of corners in the road, ping pong ball for no apparent reason. Some different lighting here, and you can see that it works, it navigates all right, and it stops exactly in the middle of the road at the end, because it's not seeing lines anymore, but it navigates to the middle. So then we did some bit more changes by sliding the viewport where the car was looking and making it a bit smaller. So we used to look at, if this is the entire image, at the bottom half, and now we'll look at make the top half but a bit smaller, so that we hope that we could navigate corners a bit. Because if you make it smaller, then it's just a corner, just a lot of small lines stacked on top of each other. So I think this is probably the end result, so the final video we've made. So sit back and relax and to see the result of our hard work. Drunk driving there, a little.
Yeah, it got a bit greedy there, cutting the line.
Yeah. That is pretty good, right? Although, I must admit, there might have been some changes to the track to accommodate difficulty the car had navigating the track. For example, it might not be a coincidence that this line is following this shade piece from the pool table perfectly. So we noticed that it had some trouble, so we moved a couple of lines a bit so that it would work a little bit better. So, okay, guilty, don't tell anyone. So this is our little project, and how many time do we have in? I think around between 80 and 120 hours.
Yeah, I think so.
I guess.
Each, yeah.
How does this compare to the real world? Would you get in a car like this, or maybe buy something better?
Right. So it's easy, right? We have our own mini Tesla now. Well, not so much. In the real world, things are bigger scale, consequences are bigger, so it's quite hard to do for real. Now, the car industry actually has some formal levels of automation. At level 0, a car does nothing. Level 1 and 2 are cars that actually can automate certain tasks. Only one task at a time, and 2, multiple tasks. So I think most of the cars we drive are actually level 2, so they have stuff like lane assist, adaptive cruise control systems, which can work in unison. Then there's level 3, where cars can actually handle dynamic driving tasks, so switching lanes, for example, or actually navigating intersections. And this is basically where Tesla's at, I think, in my opinion. So in this situation, the car still needs a driver to be able to intervene at any moment. So the icon is not really right. Yeah, so the driver should not sit reversed. He should actually have his hands on the wheel. Then at level 4, a car can officially be driverless in certain environments, and this is basically where Waymo is at, or arguably at. So Waymo this is a former Google car project. They have cars in Phoenix driving around as a taxi service. They will come driving up to your house. There's no one behind the wheel. You can sit in the back, push a button, and the car will bring you to your destination. Now, there's actually someone remote that can control the car remotely in case it's needed. But one could argue that this is a car that can officially be driverless. There's no one physically behind the wheel. And then at level 5, we have cars that actually have no controls at all. So they drive themselves, you cannot intervene. Now, there are 2 big strategies when it comes to hardware with self-driving cars. So the one big strategy is the one that Waymo is using. So base your self-driving car around a LiDAR system. And LiDAR is basically a laser-based radar system. It's augmented, or there are supplemental sensors. So there are extra sensors, there are extra cameras on the car to give it more input. But the LiDAR system is the main system that is used in order to see where the car is on the road and where it should go. These LiDAR systems are really expensive. So one of the reports I read, and it's a couple of years old, but I think the price is still pretty steep. It was $70,000 for one of those units on top of a car. So that's pretty expensive.
Just outside our budget of 150 euros.
Yeah, that couldn't be on our car, right? So this is the one. And then there's, if you look at, let me get back to the LiDAR system first. So a LiDAR has the advantage of providing you a 3D image, or somewhat of a 3D image. So that's pretty powerful. And I think that would actually help with, for example, lighting conditions, right? So driving at night, or perhaps in situations with fog, for example. Now the other side, if you will, is the side where Tesla's on. So they say, well, all this expensive hardware, that's too expensive. We do not want all this expensive hardware. We can do it with cheap hardware. We can base our self-driving system around a set of cameras on the car. And then we also have stuff like radar for seeing obstacles in front of us. But the main system for self-driving is the computer vision system. So if you're a bit imaginative, you can think it would look something like this, right? It detects the lines on the road, it detects the other cars around it as objects, and then it will base its actions on this. Now this image is clearly not a Tesla, it's a Honda, and it's taken from the website of Comma AI, which is a company founded by a hacker in the United States. He decided that, Google is doing it with the self-driving cars. I'm pretty smart, I can do this myself as well. So he hacked his Honda car, made his phone run software that could actually apply the computer vision and then decided to steer the car. And that way he built his own self-driving car, which is pretty impressive. However, the government found out and said, well, maybe this isn't a very good idea, right? To have everyone build their own systems and drive it around in the wild. So you can no longer do that. And he said, well, okay, then I will create a company that does this. So he created his company, Comma AI. They have a lot of open source software when it comes to self-driving cars, so it's pretty interesting. Look it up if you're interested.
I think the government said something in the lines of, friends don't let friends build autonomous driving cars.
Right, something like that. He said, trust me, I'm an engineer.
Yeah, sure.
So these cars are not just running around the wild, right? So the companies that actually run these or operate these cars have to take all sorts of precautions in order to keep it safe for the rest of the world. So, for example, the cars from Waymo only drive in their fully self-driving mode in areas that are pre-mapped with LiDAR. The whole level 4 autonomy of Waymo is only done in Phoenix. They're looking for expanding it to other regions as well, but they are limited to those areas. They only run in strictly defined conditions, so only when weather is fair. So it's no coincidence that these cars from Waymo operate at this level of automation in Phoenix. For one, the state of Arizona has some of the most liberal laws when it comes to self-driving cars, so it's easiest to get a license in order to do this. And the other thing is that the city has a fairly easy road system, right? So it's all pretty straight grid layout. The conditions of the road are very, very good, no potholes and stuff. So that helps a lot. They have redundant systems, so if the main computer might shut down or be no longer able to control the car, there's a second system that can bring the car to a safe stop somewhere.
Yeah, you can imagine being like in court, and then the judge saying, "So, why did you cause this accident at this intersection?" And yeah, I'm sorry, Your Honor, my car was installing a Windows update.
Exactly. So it has multiple sensors, so it can take all these inputs and then compare them to each other in order to be certain of what happens around it. The control systems are isolated, so you cannot access them from in-car Wi-Fi, for example, which would be pretty bad, I think. And the system that most of these vendors actually apply is the what I call the human intervention fallback, right? So they have this disclaimer: you can put this car in self-driving mode, but you need to be present, and you need to be focused on the road and be able to take over at a moment's notice.
So what do Tesla drivers do?
Yeah, right. So they put like it's an orange or something in their steering wheel in order to make it think that their hands are on the wheel. It's quite insane. Anyway, there's another side to these self-driving cars, and it's more of an ethical side. Actually, I think some of the ethical stuff was already addressed in the keynote that was given before this. But when we look at the ethical side, when it comes to, for example, self-driving cars, getting into situations in which they need to, well, there are no good outcomes, right? There are only bad outcomes. So what should a self-driving car do in such a situation? I mean, from humans, we expect them to act in a somewhat moral behavior, right? So, but we cannot, well, these automated systems have to be programmed. And as is continuously proven, we cannot leave it up to the industry to be moral about their software, right? I mean, we see case and case again in which we take turns with commercial benefits. So there are people doing research to this. What is moral for such a car, such a system to do? So one of the researches is done by, or in collaboration with MIT, and they built a moral machine, which basically presents you with a number of cases in which you can tell the car to take one of two decisions. So the one is the car continues on its path, right, and it has a certain outcome. And then the other one is that the car has to take an evasive action, and then there's outcome. So there's only those two, right? So we cannot tell, well, the car can stop or whatever.
We don't have flying cars yet.
That would be no fun. So let me take you to the age-old dilemma of cats versus dogs. So we have a self-driving car running down a road, and it comes into a situation in which there are only two possible outcomes. So the one is it will go straight through and thereby killing 3 dogs crossing the road.
Saving the cats.
Yeah, saving three cats. Yeah, I'm always looking at the negative side. I don't know. Anyway, so the other option is that the car takes an evasive maneuver and thereby it will save the 3 dogs, but it will kill the 3 cats. So by a show of hands, who of you would save the dogs? Right. And who would save the cats? All right, and who of you has went to the Venkat talk earlier? So he might have influenced you on dogs and cats, but anyway,
do you know
not my audience.
The amount of damage that a dog will do to your grill? Come on.
That's true. Yeah, you can look at it from the economical perspective as well. We'll see why that's a bad idea in a couple of slides. Well, but let's pick it up a notch. I mean, that was fun, right? But now let's take it into a bit more serious situation. So you are in your self-driving car with your family, running down the road. And there's again a situation which can only have two outcomes. So the one is the car does nothing, and it will go straight through, and thereby killing a family crossing the road. It will save your family, however. The other option is that it will make an evasive maneuver, which will save the family crossing the road. But the accident will kill everyone inside the car, you and your family. So now, by a show of hands, who of you would save the family crossing the road, and thereby killing your own family in the car? Yeah, right. There are always a number of hands, and I applaud you. I mean, I wouldn't know what to do myself in such a situation. But you see that it gets way more serious, right? It's your own family. And when you look at the car industry, it would be really bad publicity, right? So a Tesla sacrificing all its occupants, that would be bad. But anyway, these types of things need to be considered when writing software for self-driving cars. So not only are researchers doing research on this, but also governments see that they need to put legislation in place in order to force the car vendors to let their cars be morally right or ethically correct. And the German government is one of those governments, and they have written an old document with, I think, about 20 rules for self-driving cars to be allowed on the road. And two of those rules explicitly target these types of situations. And the first one is that whenever such a situation arises, the preservation of human life is more important than anything else, right? So property damage, animal life, plant life is all less important than the human life. So that's one. And the other one is that whenever we're in a situation in which it's basically a trade-off between the one human life and the other, the car cannot make decisions based on any personal features, right? So the car cannot say, well, this is an elderly person and this is a child, so I either do the one or the other, or based on gender or physical or mental constitution. Basically, this is a rule that helps prevent bias in these types of algorithms. So the governments are using this as well in order to make the road safer, because it's very important to do this in this field in which there's a lot of development still to be done. And a lot of development needs to be done by us as well.
Definitely. So stuff we think we can improve on. Detection of curved lanes is a whole different ballgame than detection of straight lanes. So that's something we need to work on. The line detection algorithm can be improved lots. I think the biggest game we can have is to, in some way, automatically recalibrate the video parameters and the OpenCV parameters for edge detection and line detection. For example, if you're not seeing any lines, keep fiddling with the brightness until we see lines again. You know, stuff like that. Currently, our debug methodology is the car crashes. We think, oh wow, it crashed, and then we start replaying the events in our minds. Maybe look at a recording and try to figure out what went wrong. It would be better if we had maybe some flight recorder that would store some data about why did it steer into the wall. Servos can be controlled directly from Java instead of creating a Linux, a Java system command that creates a Linux command that pipes something to a device. Don't get me started on that. It would be cool to do an experiment by using maybe a neural network to train the car to drive itself. And we would like to make it really autonomously driving by optimize it for running everything, including the entire image pipeline on the car itself. So we have time for 2 questions, which I am both going to ask to you. So the first question is, after which you've heard and all the ethical dilemmas, how many of you still want to own a car that drives itself? Okay, well, still pretty much anyone. So trust in the industry there. And the final question is, please make sure to rate this session through the Devoxx app, because we love to have your feedback on what you liked, what you didn't like. Considering the rating, be honest, but also be generous. So thanks for your time. We'll be around for the rest of the day, so if you have any questions, feel free to reach out. Right. We're on Twitter. Thank you. One more thing, everything is on GitHub. So if you want to take a look at the source, it's not too beautiful, but it's on GitHub. Thank you.